Hello, this is Mrs. Mitchner, and welcome to Calculus BC. All right, today we're going to be doing two sections, section 9.3 and 9.4, and doing some different tests to decide on convergence and divergence. So here we go. First of all, at the top of your page is the integral test. It says this: if f is positive, continuous, and decreasing. So those three things have to be true before you can do the integral test. Let me just give you a piece of advice. To decide if it's decreasing or not right here, you can always do the derivative and see if that derivative is going to be negative. If it's negative, it is going to be decreasing. So that's what you want to check for. And we're only using for x greater than or equal to 1. And it says that a sub n is going to be equal to f of n. Then the summation from I going from 1 to n of a sub n and the integral from 1 to infinity of f of x dx either both converge or both diverge. So I'm looking at this first example, and it says the summation from n going from 1 to infinity of 1 over 3n plus 1. I want to first of all think about this, since this is the first one we're doing together. Is this f of x, which is 1 over 3x plus 1, is it positive? Is it positive from 1 to infinity? And that answer would be yes. Is it decreasing? And I would say yes, because I know what the graph of that's going to somewhat look like. Okay. And is it continuous from 1 to infinity? Yes. So all three of those are true, so we can use the integral test. So using the integral test, I'm going to do from 1 to infinity. The integral from 1 to infinity of 1 over 3x plus 1 dx. Now this should be pretty much a review of what we did back in, oh my goodness, in the last couple days we've done this, last couple lessons. The limit as b goes to infinity, we're going to rewrite this from 1 to b of 1 over 3x plus 1. Okay. Now if I look at that, I'm going to be having to use u substitution. So I'm going to be letting u be equal to 3x plus 1, and du is my 3 dx, which the 3 is not there. So you can think about putting the 3 in here and then putting the 1/3 out front. So I can fix that to work. So basically, thinking of this as my u, I really have the limit now as b goes to infinity of 1/3 of, if I think of this as 1 over u and I'm doing the integral of that, I'm going to do the natural log of the absolute value of u, evaluating that from 1 to b. And I can just put my u back in and just kind of save myself some time. That would be 1/3 times the natural log of the absolute value of 3x plus 1, evaluating from 1 to b. So I have the limit as b goes to infinity, 1/3. Then I have the natural log of 3b plus 1 minus the natural log of 4. Well, if I plug in infinity for b, basically I'm just going to get right here the natural log of infinity, so we know that that is just going to be, that limit will be infinity. So therefore I can say the series diverges. Maybe I should write it out like this. Let me rewrite. Since the integral diverges, this series diverges by the integral test. There we go. There's number 1. That's pretty much how we do the next 3. So what I'd like for you to do is to pause the video, and then I'd like for you to get in groups of 4, and I'd like for you to work on the next 3. When the majority of the people are done, why don't you ask the sub to turn the video back on, and then you can see what the answers are. Okay? Don't forget to put me on pause. Okay, I put example 2 up here So I have all my work shown. So I will slide through it ever so slowly. I showed every single step to get a final answer of 1 over 72. So since the integral converges, the series will also converge by the integral test. Okay? Here is example 3. I got example 3 to converge as well. I did, on the left in the red, you will see that I went through to prove, because I wasn't really 100% sure that the what the graph would be doing, if the function would be decreasing or not. So I did the derivative and found out if x is greater than 1 that this derivative would be less than 0. So yes, f of x is decreasing. I did the tabular method when I did my integral, so that's by part in the right side up there in blue. Then in black down here I have my actual expansion of that tabular, and coming down here I got my final answer to be 2 over e. So since the integral converges, the series will also converge by the integral test. Okay, example 4, a little bit quicker. I just have 1 over n. I know it's positive, it's continuous, it's decreasing when x is greater than or equal to 0. So I just did my integral, and real quick I got it to diverge because it went to infinity. Okay, the next page, convergence of a p-series. Just very quickly looking at what a p-series is, it's the summation where n goes from 1 to infinity. I have 1 over n to the p, where p is going to stay a particular value. N is what's always changing. And if you think about this, I would have 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p. If p is going to be greater than 1, then my denominator would keep getting larger. So that therefore it's going to converge because my value would just keep getting smaller and smaller. If I look at number 2 down here, if p is going to be a very small number, say between 0 and 1, what's going to happen is my numbers are going to keep growing, so I would be diverging. The sum of the series would be, or the sum of the sequence would be getting larger and larger and larger. So think about actually putting in values for p greater than 1 and thinking about what those that sum would actually come up to be, and the same thing if you pick a p-value between 0 and 1. Add this into your notes because I don't think it's there. If p is equal to 1, it's called a harmonic series. At least it's not in my notes. I'm looking real quick to see if it's in your notes. Okay, so just make sure that you add that in. If p is equal to 1, it's called a harmonic series, and it just looks like 1 over n. Okay, so looking at this right here, these are really my favorite type because you can real quickly come to a conclusion. If I look at example 5a, I have the summation where n goes from 1 to 5 of 5 over n. So I think about this, I want to rewrite it maybe, bring the 5 out front, so I have a summation of 1 over n. N goes from 1 to infinity. I don't know why I put 5 up there. So if I look at that, this is a p-series where p is equal to 1. And more specifically, it's called a harmonic. Not that we really need to know the names of those two. So therefore, since p is equal to 1, it is going to diverge. And that's it. Real quickly, looking at 5b, I have the summation of n going from 1 to infinity. So I'm going to rewrite this as the summation n goes from 1 to infinity. Instead of 1 over the 5th root of n cubed, I'm going to write it 1 over n to the 3/5. I know you're hearing those bells. Sorry, you can't get up and leave. But anyway, this is a p-series. P in this case is equal to 3/5. 3/5 is less than 1, therefore this one is going to also diverge. Okay. Moving on to the bottom of the page. Whoops, that's not what I wanted. I don't know, I got off a page there. Here we go. Maximum error. Maximum error. If the summation of n going from 1 to infinity of a sub n converges to s, then the remainder, which is s minus s sub n, is bounded by the integral from n to infinity of f of x dx. So let's do a problem kind of talking about that. Example 6 says to approximate the sum of the convergent series. So I have the summation of 1 over n to the fifth by finding the sum of the first four terms. Now, first of all, we know it's convergent because it's a p series where my p is equal to 5. That's greater than 1. So we know that that's going to converge. Then it also wants me to estimate the maximum error. Okay, so here we go. First of all, find the sum of the first four terms. So writing out the first four terms, I call this s sub 4. That would be 1 plus my 1 over 32 plus my 1 over 243 plus my 1 over 1024. Yes, I need a calculator because getting a common denominator, wow. I get 1.0363, which is my handy dandy calculator. Change that to be 257875. 257,875 divided by 248,832. So there is the sum of the first four terms. Now, the remainder of this, so I'm talking about the maximum error of my approximation. My remainder of my first four terms, that summation, is bounded, meaning it has to be less than or equal to the integral from 4 to infinity of basically x to the negative fifth. So let's find out what that error actually is. So again, it's going to infinity, so I'm going to have to write my limit out front as b goes to infinity, and I would have the integral from 4 to b of x to the negative fifth dx. So I do my antiderivative, so I'm going to get a negative 1 over 4x to the fourth, evaluating that from 4 to b. It's really bring the negative, or add 1 to the exponent, negative 4 divided by negative 4. Then I just went ahead and wrote it as negative 1 over 4x to the fourth. So what I get here is the limit as b goes to infinity of negative 1 over 4b to the fourth minus a negative 1 over 4x to the fourth. Whoops, x is now 4. 4 times 4 to the fourth. So the final value of this, when I plug in infinity, that first one's going to go to 0. So I get a positive 1 over 1024. That is my bounds of my remainder. Okay, so that's going to be my maximum error. So if I look at this, what is my sum of the series? Well, isn't that sum going to be my, what I said, my first four terms? 257,875 all over 248,832 plus my remainder, the bounds of my remainder. So I know it's going to be less than or equal to my, again, calculator work. I don't know why I was so into getting a exact answer here. So if you have decimals, I don't think your 84s would do this, if those of you using 84s. There's approximately what my summation is, 1.0373. If I wanted, now they didn't ask me to do that. I just added that in extra because I just found my bounds is my maximum error of my approximation is 1 over 1024. I just did a little bit extra. Okay, that's the end of section 3. If you need a stretch break, you can put me on pause, take 1 minute and just get up and stretch. We still have one more section to go. Okay, section 9.4 starts here if you're keeping track of what's in your textbook. The first one we're going to do in section 9.4 is a direct comparison test. Let A be less than B. So look at that first part. That's really important to see. A sub n is less than B sub n for all n. If I have the summation of B sub n converging, then I know that A sub n has to converge as well. So in what I always think of, I don't think of like what's written there in black, I think of what's written in red. If the larger series will converge, the smaller series must also converge. And then if A sub n diverges, then the series of B sub n would also have to diverge. In other words, if the smaller series diverges, then the larger series must also diverge. So that's basically what you have to remember on that. Okay, moving on. These are kind of quicker examples than what we had in section 9.3. Determine the convergence or divergence of, and then I have example 7. Where did it go? There it is. 5 over 3 plus 2 to the n. So if I look at that, I'm going to let my A sub n be equal to 5 over 3 plus 2 to the n. And now I want to try and find something that's going to be very similar to this right here. So I'm going to let B sub n be 5 over 2 to the n. So basically just dropping that 3. Now you have to figure out which one's larger, which one's smaller. So the first thing I think about is my 5 over 3 plus 2 to the n has a larger denominator. So it's going to be less than 5 over 2 to the n. Okay? So I have to look at my, let's look at this right here. Let's look at that one. If I look at the summation of 5 over 2 to the n, isn't that geometric? Sometimes I rewrite it like this, 5 summation 1/2 to the nth. Isn't that the same thing as n goes from 1 to infinity? So we know it's geometric. We have r equal to 1/2, which is less than 1, so we know it converges. Now remember here, the B sub n, the 5 over 2 to the nth, is the larger one. If the larger series converges, then you know that the smaller series must also converge. Therefore, the summation of A sub n converges by the direct comparison test. Okay? So then let's go to example 8. If I look at number 8, I'm going to first of all try to compare it to 1 over radical n. So again, my 1 over 1 plus radical n is less than, because it's larger in the denominator, than my 1 over radical n. Now, if I think about this right side, that's a p series where p is equal to 1/2, so that's less than 1. It's going to diverge. If the larger one diverges, we have no conclusion. So we can't tell. All right? So we have to try something else. Let's try just 1 over n. If I look at this one, 1 over n is less than 1 over 1 plus radical n. Because n in the denominator is going to be larger than the square root of n plus 1. So the denominator on the left side is larger than the denominator on the right side. Therefore, 1 over n is going to be smaller. This is a p series. P is equal to 1, so it's going to diverge. So if the smaller one diverges, can I tell anything? And the answer is yes. Therefore, the series diverges by the direct comparison test. So if the smaller one diverges, so the larger one would diverge as well. And the last one in this section, example 9, let me rewrite this as the summation of n goes from 1 to infinity of 1 over e to the n cubed. That's my a sub n. I'm going to let my b sub n be equal to my 1 over e to the n. So when I compare these two things, the first thing I'm going to think about is 1 over e to the n cubed. The denominator there is going to be larger than 1 over e to the n. Therefore, my e to the n, 1 over e to the n cubed will be less than 1 over e to the n. And that will be for n greater than 1. I want to look at, what about the summation of 1 over e to the n? What is that? To me, isn't that geometric? That is geometric, and r is equal to 1 over e. Now, 1 over e is at, where does that fall? Well, isn't 1 over 2.7 whatever less than 1? So therefore it's going to converge. Now, 1 over e to the n was the larger of the two. If the larger series converge, then we know that the smaller series has to converge. So therefore, the summation n goes from 1 to infinity of e to the negative n cubed converges by the direct comparison test. There we go. There's our examples on direct comparison test. Moving on to limit comparison test. Limit comparison tests, we have two series, a sub n and b sub n. These have to be series of positive terms. And what we're going to do is we're going to find the limit as n goes to infinity of a sub n over b sub n. And we're going to find out what that limit is equal to. If L is greater than 0, then they either have to both converge or both diverge. If L is equal to 0, and if the summation of b sub n converges, then a sub n will also have to converge. And the same thing if L is equal to infinity. Okay, so let's look at example 10. I am given the summation of 1 over n squared minus 5n plus 3. I'm going to let that be my a sub n. Okay, now I'm going to pick my b sub n to be something such that when I divide these two fractions, I want to try and get the same degree in the numerator and denominator. So I'm going to let b sub n be 1 over n squared. Okay? Now, looking at this, 1 over n squared, it is a p series. P is equal to 2. So I know p is greater than 1. This is going to converge. Okay? So I know that my b sub n is converging. So let's see what's going to happen here. If I have the limit as n goes to infinity, I put my a sub n, which is my 1 over my 4n squared minus 5n plus 3, divided by my 1 over n squared. So if I divide by a fraction, I'm going to flip it and multiply. So I get the limit as b goes to infinity of basically n squared all over 4n squared minus 5n plus 3. And what do I get? I get 1/4. Now, 1/4 is greater than 0, so that would go into category number 1. Then the series either both converge or both diverge. Since we had the summation of 1 over n squared converging, where n goes from 1 to infinity, then I know that the summation of my a sub n, which is 1 over 4n squared minus 5n plus 3 also converges by the limit comparison test. There you go. Okay, if I'm going too fast, you know all you have to do is pause. Example 11. Again, I have a polynomial numerator, I have a polynomial in the denominator, and remember my hint is to let b sub n be equal to your, if you divide by b sub n, you want to try and get the same degree in the numerator and denominator. So I'm going to let b sub n be 1 over n cubed. And my a sub n being what we have up there. Now keep in mind, this right here is a p series. P is equal to 3, which is greater than 1. It is going to converge. Okay, so let's see what we get for our limit and see what category we can look at. I'm going to have the limit as n goes to infinity, and I would have my a sub n, which is n squared plus 3, all over 2n to the 5th plus 4n squared plus 1, all divided by 1 over n cubed. That limit will be equal to, flip it and multiply so I get an n to the 5th plus 3n cubed all over 2n to the 5th plus 4n squared plus 1. We all know that that limit is going to be 1/2. Yay! Once again, that is greater than 0. So I can use category 1 up there in my box for limit comparison tests. So I can say, since the summation of 1 over n cubed converges, the summation of a sub n, boy, I don't want to write all that down right now, n going from 1 to infinity, converges by the limit comparison test. There you go. Okay, example 12. Example 12 is very similar to the last two that we just did. So I'm going to have you pause and take 2 minutes and do that one, and then turn it back on and see if you got the right answer. Okay, let's see how you did on example 12. Did you pick b sub n to be 1 over n? And did you recognize that that once again was a p-series where p is equal to 1? That one will diverge. So then you divided by 1 over n, your a sub n divided by b sub n, and got the limit of n to the 4th over 5 n to the 4th plus 1, which that limit is equal to 1/5, which is greater than 0. Therefore, since b sub n diverges, the series of b sub n diverges, then the summation of a sub n will also diverge by the limit comparison test. Alrighty. Now this last one's a little bit different. We haven't done one of these for a while, so this is a good one to do together. I'm going to look at this first of all, and I'm just going to fix it a little bit before I pick out a b sub n. If I have something like this, I'm going to rewrite this as 7 over 3n. In the square root, I'm going to factor out an n squared. So then I would get a 1 plus 3 over n squared inside that square root. And since we're going to be using the limit as n goes to infinity, we're going to be taking the square root of that n squared and bringing out a positive n. So I will have the summation n goes from 1 to infinity of 7 over 3n squared, and then I'd have the square root of my 1 plus 3 over n squared. So that's what I have when I kind of rearrange it. So since I'm looking at this polynomial, this n squared right there, so I'm going to let my b sub n be equal to 1 over n squared, because I want to get that degree up there in that numerator too. So when I do my limit for this one, as n goes to infinity, I would have my 7 over my 3n squared times the square root of 1 plus 3 over n squared, all divided by 1 over n squared. That is going to change into, these colors are getting boring. Let me get some other colors. That would change into 7n squared all over 3n squared times the square root of 1 plus 3 over n squared. Now let's plug in infinity. And I think about that right there. If I plug infinity to that, it's going to go to 0. So I have the square root of 1 plus 0. So that's going to go to 1. Then my n squareds, I can think about those as canceling. So basically I get 7 over 3, which is greater than 0. Well, go back. What do we have? I forgot what we did. Oh, I have a p series again, where p is greater than 1, so that's going to converge. So since I've got my limit to be greater than 0, the summation of a sub n converges because the summation of b sub n converges. And this would be by the limit comparison test. Okay, so here we go. We are happy. We are done. That took a long time, right? So go ahead and work on some homework problems and have fun with these. Thanks for playing the game today.